Alright, today we're going to be doing basic counting principles. So let's start with a question. If we have a class of 22 accounting majors and 10 math majors, but 5 students are majoring in both accounting and math, how many students are in the class? Well, we know that the number of accounting students is 22. The number of math students is 10. And the number of accounting students who are also taking math, who are also math majors, equals 5. So the intersection of our accounting students and math students is 5. So if we want to know the number of accounting students union math students, what we have to do is we sum up the number of accounting students plus the number of math students minus the intersection of A intersect math. And that's how we would calculate how many students total there are. So 22 plus 10 minus 5, well, that equals 27. Alright, so let's think about this a little bit more picturally maybe. So if we have all the accounting students here represented here with 22 students in this entire circle, and we also have 10 students in this entire circle, and we know that we have 5 math who are in the intersection of the two, and we want to figure out how many we have total. So what we are doing when we are summing up all of the accounting students, we are adding this region here, this big old circle, 22 in this circle here. And then when we add the 10, we are adding this entire circle here. But as you can see, given that we added a blue section and we added a red section, we actually double counted the intersection region right here. Given that we double counted the intersection right there is the reason why we have to subtract the intersection of our two sets when we are trying to figure out the number of students who are in the union of the two sets. So that's how we can calculate the number of that's in a union. If we know the number that's in one set and we know the number that's in another set, we can subtract the intersection between the two sets, and that will give us the total amount. Alright, so that's dealing with two sets. Let's think a little bit more, let's make it even more complex and think about 3 sets. So set A, B, and C. Alright, if we want to know the total number that's in A, union B, union C. So we want to know total. Well, that's just going to equal to the number that's in A plus the number that's in B plus the number that's in C. So what we have done is that we have added this region. We have added this region. And we will add this region right here. And we can see that we have double counted a few regions. So we have double counted this region, we have double counted this region, and we have double counted this region. So we're going to want to subtract those 3 regions from our sum of A, B, and C. So we're going to have to subtract the number that's in A intersect B, subtract the number that's in A intersect C, and we have to subtract the number that's in B intersect C. So we have subtracted all our double counting. But if you noticed, we counted this region 3 times and then we subtracted it 3 times, so we got to make sure that we add it back in. So then finally we have to add the number that's in A intersect B intersect C. So the reason why we're adding that back in is because if we see by doing the number of A plus the number of B plus the number of C, subtract the number that's in the intersection of all 3 regions, we have counted this region 3 times, we have subtracted this region 3 times, and because we want a sum of counting it 1 time, we add it back in. So that's how we can figure out the number of that's in a union of 3. So a little bit more complex, but it's the same idea. So we're going to sum up all our individual pieces, and then we're going to subtract the areas where we're double counting, and in this case we're going to have to add in the area that we are triple counting. So let's think about another counting example. Let's say that you are at the mall, or maybe you're on Amazon, might be a more appropriate statement. So shirts come in 3 sizes: small, medium, and large. They also come in red or blue for each size. And then we are going to be interested in, hey, what's the number of combination of shirt size and colors that are available? So number of combinations we might be interested in. Alright, one way that we can do this is like starting a tree. So from the beginning, there are 3 shirt size: small, medium, large. And then for each shirt size, you're going to have a red one, a blue one, a red one, a blue one, a red one, and blue one. So we can denote from up here, this represents a small red shirt, a small blue shirt, a medium red shirt, a medium blue shirt, a large red shirt, and a large blue shirt. And then we just count up all our possible combinations. So 1, 2, 3, 4, 5, 6. There are 6 combinations. So what we did is that we went through all our available options, and then based on each option, we continue going through all the available next option. All right. Let's imagine a 3-letter code where there are 8 possible letters. So we want to create a 8-letter code or a 3-letter code, 1, 2, 3, and there are 8 possible letters to choose from. So we might be interested in the possible number of codes that could be put together under various scenarios. So let's think about the 3 specific scenarios. Let's assume that no letters repeat. So the code AAA cannot be a 3-letter code because the letter A is repeating. So let's think about our 3 letters. There are 8 letters available for the first letter in the code, and because no letters are allowed to repeat, that means whatever letter was chosen in the first spot is no longer available in the second spot. So that means that there are going to be 7 letters available in the second spot because whatever one you chose in the first one is no longer available in the second spot. Alright, so given that 2 letters have been chosen, how many letters are available in the third spot? 6. If we multiply these 3 numbers together, that will tell us the total number of 3-letter codes are available where no letters can repeat. 2. Let's think about the example where letters are allowed to repeat. So letters can repeat. So in this time, the code AAA is available to us because the letters are available to repeat. So once again, let's think about this in terms of what's available each time. So for the very first letter, how many letters are available to us? There are 8 letters available to us. In the second letter in this code, how many letters are available to us? There are 8 letters available again to us because they're allowed to repeat. And then lastly, once again, there are 8 letters available in the third spot as well. So we take the product of 8, 8, 8. We're going to get 512 possible 3-letter codes, where for each letter there are 8 possibilities. Alright, let's do a third example. No adjacent letters. Adjacent letters can repeat. So the code ABA is allowed to be available because no adjacent letters are repeating, but the code AAB is not available to us because the first 2 letters the adjacent letters are repeating. So let's think about this once again in our 3 spots. So there are 8 letters available in the first spot. Whatever letter was chosen for the first spot is not going to be available for the second spot. So that means that there are 7 letters available in the second spot. And then for the third spot, remember this just can't be whatever is available here. So we have removed one option from this third spot. So there are 7 available letters for that third spot as well. So if we take the product of all 3 of these, 392, that is the available number of 3-letter codes where no adjacent letters repeat. Alright, let's do another example where we're going back to the basic counting principles. We have set A, we have set B, and we also have our universal set. And the universal set is all those within the entire rectangle, including the overlapping circles. Alright, so let's say that some information is given to us and we want to find how many numbers of elements are in different other areas of our picture. So if we know that the number of elements in A equals 45, and we know that the number of elements in B equals 35, the number of elements in A intersect B equals 15, and the number of elements in a universal set equals 200. Alright, so I am saying that this is a given. We already know, part of the introduction of these problems is that this is some information that's already given to us. And then we are asked to find the number of elements that's in A intersect B complement. Alright, I wrote this in blue because I want to show that the region A intersect B complement, well, that's all of A that's in the complement of B. So that's like this crescent moon shaped part of A right here. Alright, and let's say that we also want to find the number of elements that's in A complement intersect B. Well, similarly, that's all the parts of B that's not in A. So we got the other crescent moon type shape going on over here. That is the area A complement intersect B. Let's say we are asked to find A intersect B. Well, that A intersect B is just this middle region right there. And the last, but certainly not least, let's assume that we are asked to find the number that's in A complement intersect B complement. So A complement intersect B complement is all of the universal set that's not in A or if it's not in B. So what that is all of the non-overlapping circles. So it's all this exterior region, you can kind of think of it. All this region here, that is the region A complement intersect B complement. All right, let's think about this. The number of elements that's in A intersect B complement. Well, let's look at a graph. That is all of A minus the intersection of A and B. So we know that this will equal to the number of elements that's in A minus the number of elements that's in A intersect B. And we know that the number of elements in A is 45, and the number of elements that's in the intersection is just 15. So 45 minus 15 is 30. All right, let's do the next one. The number of elements that's in A complement intersect B. Well, that's just going to be the number of elements that's in B minus the intersection region. The number of elements in B minus the intersection region. So we know that the number of elements in B is 35. We know that the intersection is 15. So we know that the number of elements that's in A complement B intersect B is 20 elements. All right, let's go down to a little bit easier one. The number of elements that's in A intersect B. Well, that we have already been told that right here. And so we know that there are 15 elements that's in A intersect B. All right, now let's do the last one. The number of elements that's in A complement intersect B complement. So that entire non-overlapping AB region, all that purple area. Well, let's think about this a little bit mathematically. We know that the number of elements in the universal set minus the number of elements that's in A union B. So remember, A union B is all this region right here, the both circles. So we want to figure out the total number that's in the universal set minus what's in the union, and that will tell us all that outside white space that I just drew over here in the corner. So we got to remember this will equal to, we already been told that the total number of elements in the universal set is 200, and that is going to be minus the union. If remember the very first equation that we showed to begin this lecture, the number of elements that's in A union the other of two sets is that we sum what's in both sets together, and then we minus the intersection region between the two. So the number of elements that's in A is 45, plus the number of elements that's in B, that's 35, minus the total number of elements that's in the intersection of A intersect B. There's 15 elements, and that will, this section right here tells us the total number of elements that's in A union B. So we're going to get 200 minus 45 plus 35 minus 15, that's 65. 200 minus 65 is 135. So how many? So 135 elements is in this purple region that we shaded in right here. All right, well, that does it for today's lecture.